and or Tim presenters so they can present.
They are live now.
Hi, class. Okay, Tim and Nisha are going to present from last week.
Nisha, you can start. If you're available. Okay, I'll go ahead and share my screen then. So I have a script here that I can walk through. Can everyone see? Perfect. So why is type hinting important? And it kind of goes off what was happening in last class, where we were defining functions to look at the parameters and values in our columns because we want to make sure that they're all of the same type. And so type hinting or annotation is important because Python is a dynamically typed language. This means that Python only does the type checking when it is running. And it's important in Python too, since it's dynamically typed, because the variables can change. So if I set person to Tim, or I change it down the line to person equals 25 down the line, then it would change then. And if I have it as a integer here, that actually won't work. So if I run this, this will not work because it's an integer. And so we can dynamically change the type, and in a static typed language, this will not change. You can only have it as one type throughout the entire life of a variable. And so I just have a couple examples to highlight here. Right now I'm using Python 3.7, and so I'm importing typing from the typing library, which is the basic Python, part of the basic Python library, to import a list for one of these examples. If you're using Python 3.9 or greater, there's actually a built-in list, so you wouldn't have to make this. So I have a couple examples here. I have one example of no type hinting, which is just a normal hello world. We pass a name and run it there. And then I have an example here of type hinting, so we can see that the variable that we're passing as an argument, we're passing that as a string. And then we're indicating to Python that we want it to return as a string as well. And so we can actually change this in many different ways, where you can see here that I'm actually using the list to tell Python that I want to return a list of integers. And so that's exactly what we do. And if I run this script, it would go hello Tim, and return a list of integers. And this is great. And then I can also actually, if I use mypy, which mypy is a really important thing to make sure that it's the right type here, I can use mypy type hinting .py, and it would say success. But let's say we change this to the wrong type, or we pass it the wrong type here, and I run this again, it would give us, or, oh, I need to save this, my bad. It will actually return an error message here and say, oh, we have the wrong types here. So mypy is a good thing that we can use in addition to typing in to make sure that we're using the correct types across the board. And we can include further error checking here. For example, a person, let's say I change this to 25. So that's no longer, it's still wrapped as a string because it's in parentheses here. But we know just looking at 25 that that's not actually a person. So we can actually include further parameters here, such as if name dot is numeric. Oh, I have to change this back to string. If name is numeric is true, then return none, else return hello. And so this is additional parameters that we can include to make sure that this is only returning a string, even if that string is a number inside of it. So we can include further parameters there. I can run this, and then it would return none. So that's a really quick explanation of how to use type hinting, why it's important to include it. And it also helps just visually document in your code. So if someone comes in here and sees your code, if you have the naming and other documentation there, it's a lot easier to read the code when you know, oh, it's accepting a string and it's going to return a string. Or in this case, this example here, oh, we're going to pass an integer and it's going to return a list of integers. And so it's really a powerful tool and a useful tool that definitely can help speed up testing and make sure that you're including all use cases. So thank you very much.
Real quick questions, Tim.
Yep.
Excellent, good presentation, really clean code. I've only seen this recently in LeetCode, where they define the functions like you've done it, and they actually do it at the class level or at the init level in classes. But I confess, I've never seen MyPy before. Can you tell us more about that? Is it something that comes as an executable for Python with 3.7 and above, or earlier?
So you have to install MyPy. It's a library that it's supposed to work with the type-in library from Python, or after 3.5 versions of Python where they do include type hinting, it's supposed to work with that. And with 3.9, Python has list included in it. So it works really well with 3.9 because you have all those parameters. And so it's an external package that is built to work with the existing type hints. And so you can pip install MyPy. And it's a really, really useful tool to just make sure that like if you saw, like with the example here, if I changed it, we're making sure that it's all in the correct type.
Great. And then where would you suggest, oh, let me do this. If you'll share your code with me, I'll push it to our repo for the class. And then if you could write either a markdown file or some notes directly in this code where people can go learn more about MyPy. And I'm going to let Caleb out. Keep going.
Yeah, so I will send this to Tom so that he can include it in the class repository. If there's any questions, please let me know. I'll be happy to try and assist with any questions about type hinting. It's called type hinting or type annotation if you want to Google it and do further research on it. And I will send this example to Tom so that he can share it with the class in the repository.
And let me remind everyone, this is a follow-up to our cleaning dirty data episode, and a lot of dirty data is just typed wrong. That's what happens. So that's why, Tim, we really, type hinting is kind of unusual for Python, as Timothy already pointed out. So it's really good to see it in use here. Jaya, did that answer your question? Okay, good. And then anyone else before we go to Nisha? Great work, Tim.
Yep. Thank you, everyone.
Yeah. All right, Nisha.
Can you see my screen?
Very well.
Just a second.
So you're a spider lover, I take it.
Yes.
I've heard of it a lot, but not used it a lot. It's good to know someone is using it and loves it.
So my demo, I wanted to show mainly mainly a way to figure out whether the object that is being passed is there are different types of data that you can pass, and essentially checking if it's a list, tuple, dictionary, or a set, or a class even. So I have here some use cases, not covering extensively all the use cases. So essentially, I am creating a list, creating a tuple, creating a dictionary, creating a set, and creating a class which has a set of methods. So those are just initializations. And then I am creating a set of list of lists and a data frame as well. So these are the use cases that we are going to be working with today. So what essentially this function data type check does is whether it returns out whether the data type that's being passed to this particular function is which category does it fall into. And if it doesn't fall into any category that I have declared here, it's just gonna type it as not defined. So I'm gonna run this part of the code first and then show you as to what the output looks like. So here I am passing in a list, and the list contains a bunch of strings, and that's what it's showing as to what is the item type of each of the object within that list. So we are passing it, the type of input data set is a list, and there are 9 items within that list, and each item type is being essentially defined. And this is important because when we work with data frames, and within a data frame, within each column, you want to know what kind of data is it in. And when it comes to data frame, we usually, the column takes one form or the other, the whole column. But in case of list, that is not the case. You can have a mix, and that's why this function essentially is created in such a way that you know what the type in it is, so you can typecast it if needed.
I'd like to brag on Nisha real quick in a certain way. Let's say you're looking at a column in a pandas data frame, which is a series, by the way. That one column in a data frame is a series. If you had mixed data types, it wouldn't tell you that like her routines just did. It would just say object, and it would be up to you to figure out, oh, how do I clean these mixed data types? And with what she's shown, you could do some conversions to Python objects, clean it up, and then put it back into the data frame in a cleaned up way. Very good, Nisha. And keep going. I didn't mean to interrupt. I just wanted to do some intermediate bragging.
Yes, thank you. Thank you, Tom. So next thing we are looking at is a tuple object, and same for the tuple, you can have different types within it, and this pretty much exactly does the same code. So if you look at what the inside the hoods of the function, it essentially is using the type, which is a default Python function, and it checks for what the data type is and just prints it out. And that's all it mainly does, but it's a handy little nifty function that you can use to figure out whether it is within a list, set, tuple, or a dictionary, how the objects look like. And there is also the use case of, maybe I should run all of them and show you. And this one is a data frame object. So this is going to give you some standard input from a data frame. So The data frame has what are the data types within the data frame, each column, and the first few values of the columns is being listed. That's just because I listed it out that way for my own research, just to get an idea, and I just repurposed it for this demo, essentially. Sorry about the background noise. My kids are having play date.
No problem.
And the last one I wanted to show is, we have also class type. We have a whole set of class, and we want to see what the methods are, what are the callable methods of a particular classes. So that's something useful as well, because there are so many default classes that are available within scikit-learn, other packages as well. And you want to know which methods are callable attributes of the class. And for that, this function pretty much does that. So here I'm using the is instance. So there are two ways to do it. One is to check the data type, and the other one is checking if this particular instance of the object is a data frame or a class. Then I am essentially printing out the class, and I'm using a method of calling an attribute. So if the attribute is callable, then I am listing all the methods that are essentially callable. So this will not give you the other attributes, like the within a class you initialize it. Those kind of things will not be returned. This mainly gives you the callable attributes, because that's the one we commonly use in our Python coding, essentially, when we are trying to define something or call a particular instance. That was pretty much my demo. One interesting thing that I learned was, when you create an instance of the class that you have, or a default class, then if you do a data check on the class, that way as well, it shows that the class type is a class, essentially, here. While in the other case, it's a definition of class, it's a master Python type, which is called type. So any object will have a master, we will have a master type called type, actually. I don't know how else to say it. Maybe Tom can say it better. But if you're actually wanting to know if it's a class or not, then you have to pass an object that is instantiated for that class, and then pass that object to the data type check function that is defined above. This is already in Slack. If Tom wants, I can send the code as well to him.
Yes, for sure. And I want to give a shout out to, integrating brilliance. Most of you've heard me give that talk. Let me explain how I would integrate Nisha's brilliance this morning. We hear about data visualization, but how do you code visualize? Now, Nisha is showing a lot of great work, and I understand it would be hard to ingest it all at once. So if you wanted to understand her code better, you'd take it a bit at a time. And a big thing that I'm a fan of, I'll write it right here in the chat, is sys.exit. So you, up above, you would, I shouldn't have done that just yet, but import sys above that last statement. And then somewhere down in the code, you do a sys exit. So it just graciously stops at that point. But above that, you put a lot of print statements just to visualize what's happening in greater detail, so you understand it at a step-by-step. There was so much good coding in Nisha's code, and so much operational detail, that after you clone or download her code from the repo and play with it, you'll see more. But I want to remind everyone, this is still part of our data cleansing work. And this stuff's necessary for when we're just trying to, say, automate our data cleansing. But a lot of that, again, is getting the right type set. Thank you, Nisha. Did anyone have any questions for Nisha before we go on? Yes, Jonathan, please.
Yeah, so that's, really enjoyed both, but this one's for Nisha actually. When you can look at the data frame and it looks through the series in the data frame, and that's just a small printout. I guess you can extend your code to show maybe set particular rows that are, as opposed to saying item 1, 2, 3, you could take the iloc and say iloc is a string. I guess you could extend it that way, and you could probably summarize it to say X amount of rows in X amount of float within that one series. Just because I can imagine when if you've got like a huge data set and you've got all 5,000 lines to go through, you'd have to adapt it in some way to make it more direct, visible for yourself.
Yes, I completely agree. This is intended to be for a small data set. The bigger data set, I can see your point. Yeah, this can definitely be extended to do that.
I would say that Nisha's code is a great launching point for many other routines down the line. These both of your works this morning, I liked both your works. Tim was unique in that he's introducing something, and by the way, that type of scripting that Tim did, that's what I put in my Tom overflow directory. I have tons of stuff like that, probably not as neatly coded because it's really sandboxy. It's very sandy. Okay, I will present. Let's see. Gotta find the right one. I have so many things open too. I don't want a particular screen. Okay, I may have to go hunt for it real quick. Hang on. Oh no, that's it. Oh, it was hidden. All right, I'm going to do a side view then, so I don't slow us down too much. Screen 3, excellent. Okay, there we go. So I'll be looking sideways to y'all, sorry for that. Okay, I want to do a quick, you'll want to do a new pull, and it's at the integrated machine learning and AI repo now. If y'all don't have that, I'll try to get it here in the chat soon, but make sure you do a new pull. And I've tried to clean this up for you guys a bit. These two functions here, and let me make this bigger. We don't need to be that small. Let's see, Control plus. There we go. That's probably good. Okay, each of these correspond to one over here. And I'm going to add more, like this one goes with this one, etc. If you see additional numbers, it's because I haven't put something with them yet. If you see something without a number, it's just meant to be an example. And I'll try to clarify. Guys, could you check on Ambrose? Sorry for that. No, he's scratching at, sorry, my border collie never does that. I don't know what's going on with him. I'm sorry. Sorry, guys, that is very uncharacteristic. No, not now. Someone come get Ambrose for me. He's being weird. So sorry, guys, that is really unusual. But I wanted to remind you, here we're creating data. Oh, and these were the ones that I presented last time. These are NumPy based, excuse me, wrong. These are NumPy based, and I will soon create some models for those so that we can start looking at some basic classification modeling. But to get ready for the lecture today, I wanted to re-illustrate these real quickly. So I'm going to rerun this one, and it's going to present the data both in the output and here in this plot. And it's also saved it to this, if we look in the code, it tells us that it saved it to in this directory and in linear data.csv. So it's right here. Now, if I go and do a subsequent model to fit some of that data with the test train split, I go over to this file. I'll kill this terminal, and I will just run this model now. And you'll see that it's going to load the data. And forgive me for not going through the code. I will show some of it, but you see the blue dots are for training, the red dots are for testing. And when I close that, it continues to run the code, and it shows how it fit. The red dots have now become blue dots, and the red line is showing the regression model that fit through there. And so important points here. You can see that here is my model coefficient. But if I go back and look at the model file, well, that is indeed the slope I had. And I've even got some noise here, but it still got very close to the model parameter, because the noise is just not that large. And it's a very simple model. So, but I want to focus here just briefly on, well, what did the code look like? Of course, we're loading the data here. We're defining the column names because it didn't have column names in the data file. Then we're just converting it to NumPy values. That's what this part does right here. Then I split it into features and labels here. Now, if you're unfamiliar with this NumPy splitting conventions, it's basically just row, comma, column. If it were multi-dimensional, it would be the next element or the next axes, and there can be multiple axes. It can be hyper-dimensional, way beyond 3 dimensions of this. But we're just using rows and columns right now. And so this is all rows in the last column. Please come off mute if any of this in NumPy is confusing, because if you have the question, I bet others do too, but you can probably also find some good material online. But understanding NumPy well is part of what we want to do. And I know we've been through it a few times though. So, but that's not to hint that you shouldn't ask your question, because it can mess with your mind until you get used to it. I believe we've talked about these in the past, but the main thing I wanted to point out is this is where all the magic happens. This is where we instantiate the linear regression library and we do a fit. But you know, I could put a bunch of these, of different model types for regression, not just linear, but I could use decision tree regression. I could use random forest regression. I could use AdaBoost, XGBoost. There's all these different algorithms. You could put them in a list and define them all to model. And I just want you to see that. But also up here, where we were defining what is X train and what is Y test, well, we could change that. If we had a bunch of columns and we just wanted to do something unique, we could say, well, I want this to be the label right now, and I want all these other columns to be the features. So, and then whatever you define to be your X test in that group is the Y prediction. Now, in case I'm losing you, I'm going to give some graphics of that. But I want to run back through to show you something really interesting. We'll jump all the way down here to this fake double feature nonlinear data. So I'm going to create 1,000 points just to make this more clear. And let's look ahead of time at my model parameters. I've got 0.36 times all the x zeros squared, and I've got 0.0324 times all the x1s cubed. And I'm going to put in 4 for my amplitude of noise. Again, this -5 is just to say, well, the data I'm going to get back from this is from 0 to 1. I'm going to make it go from negative 0.5 to 0.5, and then I'm going to make it even bigger. So I'm going to say 5. And so when I run this, it's going to restore that data in a new format. Looks like someone has a question. Oh, it's me. Maybe I should lower my hand. And I am trying to, oh, when it goes into this mode, it throws me off. Let's see if I can lower hand. Excellent. Okay. Now I'll bigify this so you can see that, yes, it's a bunch of individual points, 1,000. Okay, so I'll close that and we'll finish that. Now I'll go get its corresponding model file. And let's look briefly here. I'm just loading the data. I'm converting it to values. I'm splitting it into labels and features and labels. But I'm making sure that I create all the features I need. So I've got just the x zeros. I've got the x zeros squared. I've got just the x1s and the x1s cubed. Now, this is presuming I did some feature engineering, which we haven't talked a lot about yet, only at a high level. But let's run that and see if I get the original model weights that I modeled my fake data with. Okay, so we'll show, and you can see the red dots sneaking in among the training dots, the red dots being the ones we'll test with. And then you can see the fit of the data here. But what I want to show you is, look, we got pretty close to those model parameters plus some noise, but I'm not exact. And why am I not exact? I hope it's obvious that it's because I have this noise and I only have 1,000 points. So here is where we expected to see the 0.36, and I'm not exact, but I'm close. And I shouldn't have anything for the x zeros. But then for the x1s, I get this, and I don't quite get to the 0.32. So, well, I'm just curious. What if I drove this to 0? What would you guys expect? Well, let's just see what happens. We'll run that again. And you can see, well, I don't have any noise. So everything's following a very tight line. And so I've generated that new data with no noise. Well, with that new data, let's rerun. Okay, so I do this, we can't even see the red dots mixed in with the blue, but they're in there. And then we do the fit, and yeah, it's pretty perfect, but what do we see with the model parameters? Right here, well, that's pretty darn near 0. I hope no one will argue with me on that. Here's our 0.36. Here's another 0. And here is our 0.32. It's 0.324, excuse me. Look how exact this is. And that's because we have no noise. So it's the noise that actually obfuscates things, even to the point where if you had collinearity, it can be hidden by the noise. Now, this was all a quick review before we go in to our lecture for today. So let me go to that real quick. And I want to illustrate this. Can everyone see this okay? Just need one thumb. Yeah, good. I see a head nod. Okay. Now, again, let's say here are our features. Now, this is all of that was a review to help you appreciate what we're going to talk about now. So here are our labels. that we've decided these are the things we want to predict, but we want to train a model. So we know all these labels so we can train. And these white areas represent missing values. And feature 7 has just almost no data. So, and come off mute, anyone give me a good guess what we should do with that feature? Or you can say it in the chat too.
Drop the column?
Drop
maybe?
it.
Thank you. Yeah, I mean, it's a travesty, right? But what can we do? There's just too much missing data. So I drop it. Now, boy, the modeling could be so much more valuable if I had this data. So what can I do? Any ideas?
Imputation.
And how would you do that, Jonathan?
You could one, you could summarize the column and impute the mean or the median, or you could look for if there's any other connection between other features and then group and take the mean and median to impute.
Exactly. Now, what does Jonathan mean, someone else, when he says impute? We could even say infer through modeling. What's he getting at? Anyone? Okay, I'll answer it with the next slide. This is what I meant. We don't have to be forced. I mean, remember when you go to Kaggle and they say, here are the features, here are the labels, that's a lot of pre-work. I mean, obviously, if you're looking at the Titanic and you're looking at survival rate, it's pretty obvious what the labels are going to be. But out in the wild, out in the real world, where you've been looking at data most of the time for your company or your organization, now you have to decide, well, I've been looking at data for a while now. You know what? It might be really good if we predicted this data that comes in later than the rest of it. If we knew a prediction of that before it happened, it would really help us, like churn. Are we going to lose a customer? Can we predict which customers are likely to leave? Let's predict that. But until you get there, you would really like to have more feature 6 data. So what I can do is say, I'm going to temporarily treat this box right here as my training data. And this will be my test data. And these will be my labels. And I'll predict these missing ones. Now, think about with me, why did I not just use these 3, because they're complete, to predict this one? Any guesses? Well, it's because it wouldn't necessarily be as accurate, right? So I'm being very careful here. You could try that, but again, you'd have to experiment to see which way was more accurate. So once I do this modeling to predict these missing values, and this is assuming I should predict them, it could be that based on the data type, I should just, by the way, you do this with classification or regression, but it could be that maybe I should just put averages in. Maybe I should fill it with zeros. You have to know your data enough to know. But this is when we've determined, yep, I want to infer, I want to impute, I want to predict what should be there. And a lot of people do this, by the way. So now I can say, I should have done a different color, but I'm saying these are the predictions and they filled the gap a little. But now what can I do? I'd like to get still more. Well, I decide, okay, I'm going to use these 4 features, this much of these 4 features, and this much as test to predict what should go here with these as the labels. Now, why did I choose to go deeper on feature 5 than feature 6? Does anyone have a guess as to why I might do that?
You're filling in like backwards the steps. So feature 6 was the most missing. So you brought that in line with the top. So you brought it in balance with the other features. You're going to take now feature 5, bring that in line. Then you can probably go back to predict the rest of feature 6 and keep that pattern going. That's my guess.
And that's not a bad guess, but what I really want to do is figure out, hey, which one between feature 5 and feature 6 is best to go deeper with next? And how do I do that? I ask myself, well, if I just use features 1 through 4, do they tend to correlate stronger with feature 5 or feature 6? And whichever one has this, whichever feature 5 or 6 correlates most strongly against features 1 through 4, I start with that one because it's already telling me I'll get better accuracy for that one because I already know there's a strong correlation there. That way I lead with the, so I could have said, no, use feature 6 as the labels and fill in here. That is, if features 1 through 4 had a conglomerate better correlation to feature 6 than 5. But I'm actually saying, this is all fake, of course. I fakely did a study to find out, no, these all correlate strongest to feature 5. If I do that first, then I have a better chance of being more accurate for feature 6. So I go on ahead and do that prediction, and I get that new. And again, I'm deeply regretting I didn't make these a slightly lighter color of green now, but I just didn't think about it at the time. I was on a roll. Okay, now I say, well, I want to go deeper on feature 6, so I do that and I fill it out. Well, now I still have some more to go, but it's that same question again. Which of features 4, 5, and 6 are going to overall correlate best to these first 3 features? Whichever one it is, that's the one I do first. And then when I fill this one in, I say between these two, which ones of these strongly correlates overall to the other features? And so I keep going. Now, if I do this a little bit of time, I can just get it all filled. This is assuming they're the type of features that you can impute on. And at that point, I want to stop and ask, are there any questions? Okay, now.
So Tom,
yes.
when you're filling the features, right, the empty ones, are you just taking the average of the first 3 or first 4 as you're going? Is that what you're doing?
Let's go back a slide or two. So do you mean like?
So you're taking, if you stop there, are you taking like 1, 2, 3 and taking an average of those and filling out?
No, now you could do that, but what I'm saying is these features are used as features in a modeling exercise.
Okay.
They're the inputs, and these would be the outputs. And then once I've trained the model with these as the inputs and these as the outputs, I can now use that trained model with these as the inputs and predict this output to fill in that missing data. Good question, because I bet a lot of people might have missed that same point. So yes, and then each time I'm just very carefully, now Jaya, these are my inputs, outputs that I train with. These are the inputs I use to predict these missing outputs.
Got it, thank you.
Yes, you're welcome. Thanks for asking that question. Now, this slide is the slide that Tina uses when Tina and Lewis and I present on supervised machine learning pipelines. And you can see, well, this is a really good graphic from Medium, a Medium article on, I'm pointing with my finger, that's not going to work. How do we handle missing data? Well, sometimes, like we saw at the beginning, we've got to delete it. And sometimes you can get by with just deleting the rows. But sometimes you have to delete a whole column. And sometimes there's pairwise deletion. So there's clever ways to go about that deletion, but that's usually what you're going to look at first. You're going to triage what's so bad you've got to trim it. I mean, that's like gangrene data. There's so much missing. Now, obviously, what we just went through would be imputation in a general problem where you can do that for categorical or continuous, that is classification or regression. But if it's time series, you just got to go at it a little more carefully. And it's not that you can't, by the way, let's go back and look at something. Go back to the very first picture right here. The data may not look like this, but I can organize it this way. If it's regression or classification, I can sort the rows so they look like this. So that would be a good data cleansing tool for a data frame, to sort your rows so they show up this way. And then I will, over time, show you some routines that I've written in the past. I just don't want to get ahead of ourselves. You can see this is part of the acyclic nature of what we do. We haven't taught modeling yet in detail, but we're teaching modeling here to deal with missing data. You know, it's kind of unlucky that way. But we really can organize our rows this way, even with time series. It's just that before we do a prediction with time series, and we're using time series type tools, we've got to put it back in a time series order. Make sense? So just wanted to point that out. So let me go back to this slide now. So with time series, you've got data without trend and without seasonality, then you can, that's okay to use these types of methods or a sample imputation. So mean, median, mode, random sample imputation, things like that. But this is where you get really lucky. If you can do linear interpolation to fill in the missing data, oh, thank you. That's not that bad of missing data. That's easier to deal with. And then data with trend and with seasonality, you can do seasonality plus interpolation. So, but again, take time to this is a good soft skill with data. Seek first to understand, then to be understood. Because you know what? The data's not going to try to understand you. But if you understand the data, then you can make it understood to others at least, okay? And so you get to know your data. That's how you know how to deal with the missing data in these senses. And with that, I'd like to stop presenting and take questions. And I can put those images back up too, but any questions? And sorry for jumping ahead like that, but if you do go through the code that we showed, I tried to make this really fun to break down the way I was describing, like I was saying with Nisha's code. I've tried to just make this in really clear sequential blocks. This isn't dealing with dirty data here, of course. It's just trying to illustrate. I used this to illustrate this morning. I can create data, but then when I go use it, I've got my features here, and it was just to illustrate that one picture where, hey, we can redefine what are features and what are labels. That's all I was really trying to get at. Okay.
So Tom, the features are actually the columns of a data, right? They are considered the columns, correct?
In fact, yes. And in fact, even the labels are columns. You've just decided, Jaya, okay, this column, I'm going to call it labels because it has the data I want to predict. This data, say, comes in later as a result of these columns. And I figured that out after studying the data and the business problems for a while. So I say, oh, well, I've got to get rid of that one. Now I want to fill in this one. So I'm redefining this label as is meant to say, these are the labels now. They're still called feature 6, but ultimately it's because this is part of a problem where this will be the labels. But right now, just for filling in the missing data, this is my training data up here. this is my test data, but I'm using it to predict here. It's like I'm doing a very unique train test split and redefining what are labels just to predict this little missing part.
Okay, thank you so much.
Yeah, yeah. Any other questions, guys? Okay. I like to be sensitive to the fact that we are biological entities and might want to take a break before mentoring. So I'm really glad all of you could come. If there was, and don't be shy about sending me a private question on Slack either. And hopefully see you all in mentoring. And I'll hang
Bye.
out.
Bye.
Bye, everyone. I will hang on in case someone